that was kind of abstract. We don't know what the vector space is at all. We don't have a clue what the field is. We don't know. But what that statement says is that if you have any collection of linearly dependent vectors, then there's one that can be written, or a list of linearly dependent vectors, then there's one that can be written as a combination of the ones before it. And it says that you can remove that without changing the size of the span. Okay, so what we're going to show now is also very abstract. And I understand this can be difficult at first because we don't know where we are, but there's a nice thing about proving things like this, and that nice thing is that, well, we can use it all the time. Because we're proving it in the most abstract setting. So suppose that V is equal to the span of some vectors, W1, W2, through, and I kind of want my notation to match, Wn. And suppose that V is equal to this span here. And also, suppose we have some independent U1, U2 through UM are independent. I'm not going to squeeze that over at the edge of the paper like that. Okay, so we have some independent collection of vectors. Then what can we say about the size? Well, if this is an independent collection that happens to be in V, then what do I know? Well, I know that the linearly independent list has fewer elements than the entire list of vectors that we're using in order to create the vector space V. So we have some vector space V that's created by W1 through Wn. If I take any independent collection, so some independent collection of vectors, the size of that list is going to be less than the length of the number of vectors in this span. Okay? So that's what we're showing. Okay, so how are we going to show this? Two parts. So what we could do, and what we will try to do, is we're going to try to replace these vectors here, the w's, with the u's. So I want to replace the w's with the u's. So what I'm going to do now is I'm going to say, okay, consider, and let's write proof to start ourselves off. Proof. Okay, so what we're going to do is we're going to consider the collection, consider with an R, the collection U1, W1, W2 through Wn. Okay, now what do I know about this collection? Well, I know it's dependent, which is dependent. How do we know that? How do we know that? Well, U1 happens to be in V, and V is the span of these vectors. So I know that U1 has to equal A1 W1 plus A2 W2 plus ... plus AN WN. Okay, so since U is in V and V is the span of these vectors, we can write this U1, as a combination of these. So this is going to be dependent because what do I have? Well, by my definition of dependence is I can do this. And I know I have written 0 in a non-trivial way because this is not 0. Right? So this is a dependent collection. Okay, so now what can I do? Well, since this is a dependent collection, I know that there is some vector here which is equal to a linear combination of the terms before it. So there is some wj which is equal to the previous terms. So by our last result, there is some wj equal to a combination of terms before. So what can I do? I also know that I can remove that without changing the span. So V is equal to the span of U1, W1, W2, Wj minus 1, Wj plus 1, all the way through Wn. Okay? So notice that this list has the same number of elements as before. We removed one thing there and we added one thing there. So the length of this span is unchanged. There are still n total vectors. Let's use the correct word. In terms is okay. It works as well, but let's be specific. Okay, so we have n total vectors here. And what we can do is we can repeat this for each of the u's. So we got u a spot on the list. U was trying to get into the club. It made it in. We got to do this for the next u, and the next u, and the next u. So we're going to repeat for u2, u3, all the way through um. Okay? So each time we're going to do this. And each time we're going to remove a w. Wait a second. How do we know we're going to remove a w? How do we know we're not going to remove a u if we keep doing this, right? I mean, it's obvious we're not going to remove the u the first time we do this because there's only one u there, right? But once, let's say there's hundreds of vectors in both of these lists, and once I get to, vector number 576, how come how do I know I'm not going to get rid of u576? I'll tell you why. Because the u's are independent. So we can't write any of the u's as a sum of multiples of the other terms. It has to get rid of a w each time we do this. And that is key. We're using the fact that the u's are independent. We better, because that's our hypothesis, right? If we were able to prove this without showing the u's or without using the fact that the u's are independent, we would be in a lot of trouble. That would mean we just made a horrible mistake. So because the u's are dependent, I can do this again and again and again. So I'm going to repeat this, and what am I going to have? I'm going to have V is going to be the span of U1, U2, ... through UM, and then some collection of W's. I don't know which ones. I'll have W, and I have to get weird with my indices for a second. I apologize. I'll say W, I don't know, I1 and W, I2, all the way through W, IK. But what do I know about the number of terms? There's still n total vectors. Okay. So what we did is we started off with a vector space, which is the span of W1 through Wn, and we were able to rewrite it as shown. Okay? But what do I know here? Well, there are n total vectors. If m was bigger than n, it doesn't make any sense because this list contains u1 through um. So m has to be less than n if there are n total vectors, and u1 through um are all on the list. And that's the proof.